me just double check that I got my microphone on. Microphone's on and we're ready to go. First things first, I'm just going to set up console. What I thought we'd do today is hit a classic example, which is Hertzian theory. Now, originally the idea of this is contact analysis. This is looking at the way that two bodies interact. And Hertzian, let me just double check my notes. I'm sure Hertzian's original idea appeared in the 70s. Let me just double check. So it's the rises. Yes, in the 70s. And what we're going to do today is pull some of his classic theory and we're going to try and see if we can get solution. Now the idea with this is dead simple. We are looking at elastic behaviours and we're looking at two bodies interacting. Now if any of you already know the Hertzian problems, you'll know a few of them. So one will be a cylinder on a cylinder and the interaction of faces, and more importantly that surface area that's interacting when they hit with each other. The Hertzian theory of contact, he focused primarily on non-adhesive contacts where no tension forces are allowed within that contact area. And the assumptions that he makes and the assumptions that we will make in this are as follows really. The strains are small and within an elastic limit. Each body in this case will be considered elastic in a half space, and the surfaces are continuously and non-conforming, and all bodies in this case will be considered to be frictionless. That's just explaining to you that these are the limitations, the assumptions that we'll make within it, because obviously you'll come to the end of this and say, well, yes, but what about the contact friction? What about the wear rates that are occurring? What about the resistance of the two materials? In this case, we assume zero friction. The theory of contact between two elastic bodies can be used to find indentations, depths. It can be used for hardness testing. It can be used for all sorts to really establish the strength of a particular material. What we'll be doing is using what we call a spherical profile on an elastic half. Basically, we're going to be using half a circle, if you will, that hits a flat plate. Then what we'll do is we'll build in our theory onto it and we'll see if we can get something similar by using it. Granted, we'll come to the end of this and there's always room for improvement, But one thing that we've not done in these notes in particular is we've not looked at contact. We've not looked how bodies can interface with each other. And also everything we've done so far has been 3D. If any of you are familiar with Hertzian, you'll know you go from your classic contact of sphere to half space, through to sphere onto sphere, and then you can go to your three-dimensional profiles where you've cylinder to cylinder contact, and it can go on and on and on. But I thought what this would be nice to do is just to start on the dead basic version, which is the earlier system. Well, not earlier system, I should say that it's the basic profile. So what I'm going to do is I'll create some notes to support the theory behind this, because what I'm going to do is build the theory into this, then we will build the model, and then we will look at the comparative between the two, see if we've got any verification there. If we've got error, could we theorize why that error's there? So let's get into it. So first things first, I'm going to go to the model wizard. Now we've conventionally stayed around three-dimensional. What we're going to do in this case is go two-dimensional. In my case now, I'm going to go to solid mechanics. I'm going to add that in. Come on, no. I didn't think it was ever going to work then. I'll go study, and I'm going to go stationary. Now what we're going to do in this is we're going to do something really sophisticated. We're going to use a parametric study to systematically move it, and then we can look at what's occurring throughout that rise of the stress. See if there's anything there. I mean, in this case, there isn't much, but it allows you to see the idea of having variant sweeps without even having to go into time-dependent responses. Time dependency is something else. We are going to do that because the beauty is with YouTube, the beauty is with what we're doing here, we can go crazy and look at different options. So let's go to done. And like magic, we've got our first profile. What we need is we're not going to do hand drawn, and we're not going to waste our time with hand drawing. What we're going to do is build in our conventional things, and also in this, what we're going to do is we're going to make our own material. Now the beauty is with this is we don't have to say let's make it steel, let's make it aluminium. We can choose the variants of the materials, we can see what happens with it. And I mean, what I would like to do is actually build this as a physical test as well, and then we've got the overall. It's super exciting, super exciting. Okay, first things first, what we need is we're going to go to global parameters. Global parameters are amazing for things like this, because if you're building in, oh excuse me, oh goodness, if you're building in new types of materials and you want variations, then this is how it's done. So first things first, what I want to do is I'm just going to establish my Young's modulus. So I'll call it E1. The reason I'm calling it E1 is because, don't forget, I'm going to have two bodies there. If I want them to be the same, I mean in this case, let's make them the same. Best way forwards, but let's make them the same in this case. Let's run it through, so we'll go 2 E09, and what we'll say is, let's call it cylinder material. Let's call it radius material, because really, well, let's go circle material. We'll get there in the end. Circle material. Let's go E2. And for this, as I said, I'm just going to keep it the same. You can change this, it's purely to you. And we'll call this, now if I remember, you see I do have this written down in bits. Now we're going to call this elastic half material. Elastic half dash material. Right, so we've now got both material sets there. Now, in any case, what do we need? I can hear you screaming at me already. Why have we not got Young's modulus? Why have we not got the Poisson's ratio? Right, so let's go Poisson's ratio. So what I'm going to do is to conform to the equations. If you've pulled the notes, which by now should be up there, if they're not, please say why have you not put the notes up yet. I'm going to call this is going to be, because in the Hertzian problem, the Poisson's ratio is actually noted as V, and so what I'll say is, let's go 0.3. Let's call this Poisson's ratio. Now what will help with this is if I, let me look, if I just name this to be specific, because you know what it's like, you look back and go, what was that again? So if I say, we'll call this circle, and it doesn't need to be more than that, so I'll go V2, 0.33, and we'll call this Poisson's ratio elastic half. Elastic half. Okay. So now we got in there, we've now got our material properties. Oh, tell a lie, there is one material property that we still need. We are going to need the densities. For our calculation, we will not. But for our simulation, we will. It will need to know what the density of that material will be. It's part of the elastication process of what we're looking at. So we're going to go D1, and let's just make one up. Let's go 8 kg. Let me think. Slash meters cubed. Close that off, and then we're going to call that circle density. And then we'll do the same again. We'll go D2. We're going to go 8 square brackets kg. Oh, kh, kg. Tell you, up here for thinking, down there for dancing. Right, and we'll come back again, and we'll call this half elastic. We'll call it elastic half density. It just allows us to trace back. Super easy trace back. There's a few variables I want to add, but I'm not sure when. The other thing is about our condition. Let's set a force. So what we'll do is we will go force 250. Yeah, we'll go force to 250. So we'll go force. We're into force. 2 minutes, guys. I just need to check something. Right, so sorry about that, gents. Ladies and gents, I should say. I just needed to nip out to the loo. So, where were we? Oh yes, we're on to the force. So I'm going to put 250 newtons of force on there. I am plucking these values. Oh, excuse me. The other variable that we've not set yet is we've not set a radius for our impending cylinder that's impacting. So I'll say R, which will become my radius. And I'll set that to 25. What you should notice at the minute is I'm not really setting units here, because if I put the units in when I push past these through to equation, it does not like the units being there. So if you're going to do verification equation there, that refer to non-dimensional aspects through to dimensional aspects. If anybody comes across a good solve for that, please let me know, because it's one of those things where you sit there and go, I'd like to do that, but it's irritating me why it won't do that. So I'm going to, what I'll say is, this is the radius of the circle. So that's the radius of the circle. If I make any spelling mistakes, by the way, please someone tell me, because I'll look and go, yeah, that looks alright. It'd be completely wrong. So I'll do H for my height. Now this is going to be my base target. So I'm going to do the height. Let's go. Let's go 30 millimeters. So I'll go base height. No, it's actually not base, is it? It's elastic half. Elastic half height. H-E-I-G-H-T. Getting there in the end. Thank you, ladies and gents. Right, so then I'm going to do a width, and we will say that this width, I don't know, we can go quite crazy with this one. So let's go width of, I don't know, 80. So it's a nice width between it, and we'll go elastic half. Hard. Width. And then we're in. Right. So I have to keep checking my emails as well at the same time. So we've got his width, we've got his radius. Trying to think if there's anything else I'm missing. We're going to come back to adding in the calculation. All I want to do at the minute is I just want to make sure that I've got all my geometric references in there. So what I'll do first is I'm going to go in there and I'm going to go to my geometry. What you'll notice is I'm instantly on a grid. doesn't need a plane. We're ultimately in a plane. And it notes length and width. Now you'll see here, if I go back to here, you'll see that I didn't put units in. If I go to my geometry length units, whatever I choose it to be, it will scale itself, which is quite useful. This is another reason why I'm doing it this way, actually, just because it does make life easier for being able to control things. So let's go to geometry, and what I'm going to do is place a circle. Circle, put it anywhere. This case doesn't really matter, because what we're going to do is we're going to settle that to 0, settle that to 0, and then let's build again. So 0.55 millimeters, definitely not that. So what we're going to do is say R, build again, scale it. So we've now got our R. Right, so we need to move up in Y, don't we, if you think about it. We need the circle to move up in Y and then actually move up by half of that width. Because what I'm going to do, well, I'm going to do it this way. You don't have to do it this way, but I do it this way just because I don't like it getting all messy and all over the place and just crazy. So what I'll say is we're going to go R plus H. We'll go comment H 2. So then the half elastic will scale itself from 0. That's my plan. So I build that, and that's where it sits. So let's go back again, and then what I'm going to do this time is I'm going to add, let's just add a rectangle. And now it's asking for, where's my rectangle? Because I clicked on it that way, let's just put it in. Let's just not mess. So what I'm going to do is go W, and I'm going to go H. Did I go width? Oh, wait a minute. Did I go width and height? I did go width and height. I was starting to question myself then. So that's in there. Let's go build. Right, so that's where we sit. So what I need to do is I want this to be moved back by half. So I know by that I can go W over 2. But if I do that, in fact, let's follow build. And you go, oh, that's not what we're after. In fact, that's not even the right spot I was going for. So we're going to go W over 2. And that's where it puts it. You go, okay. So what I'm actually wanting to do is I'm actually wanting to go half W over 2. Like that. Because what it does, if you remember, if you look there, we have 0 and we have 0. So what it's doing is it's operating around here. And I'm saying half of that way, bring that point over. So it's brought it halfway across, which is great. So now what we're going to do is we're going to do the same thing. I'm going to move it down to make it so it's in line with my cylindrical face. So it's got that interface. So what we'll do is we will go minus H of 2, and then we rebuild again. Now, you look now, we've got that classic shape, that classic cylindrical shape, well, that classic circle to the rectangular interface. Right, what I want to do is just confirm my geometry. So I'm going to go into my geometry and it says, how do you want it? I'm going to make a union, repair tolerances. I'm just going to make them relative to a particular size. Just because of what this problem is, it can prompt problems if you do it as an automatic. So I'm going to go relative and build it. So that now is my Hertzian test set. Right, as I said, I'm going to produce some notes to support what I'm just about to go through. So, what I'm going to do is, I really want to know the stress, and I actually want to know my tau max, my maximum stresses, because that is what I'm going to be comparing against. First things first, I can measure the level of indentation. I can look at the stiffness. What I'm actually interested in is just pulling the stress and the tau max. So I'm going to call this AC. Hang on a second, let me just bring this up. 2 seconds. There's always one particular symbol that always eludes me. Well, not eludes me. I always get mixed up with, and I always want to call it sigma, but is it sigma? It is sigma. So it's actually sigma C. Let's do it right. Let's do it right. Let's call this sigma C. So we'll call that sigma C. Ah, it doesn't. I'll go undercase. Underscore. Right, so this is calculated by saying 0.4 multiplied by, now you have to follow me with this, bracket, bracket, Young's modulus, all squared. I'm closing the brackets because this is part of the equation, multiplied by my force, all divided by my R, all squared, and close my brackets, all to the power of 1 over 3. Now, the reason I'm going back is because you'll realise there's all this nastiness going on over here. So what I'm going to do is I'm actually going to close off my upper comments here to make them separate, because as ever, this system isn't happy. So that's 4.6 to the 4, is that megapascals? No, it's Newton meter squared, isn't it, that? But what I actually want to know is my tau max, which will give my maximum contact force, stress. So I've got tau max. And because it's a classic solution, what we're going to do is we'll say, let me think. Oh yes, of course. Going sigma, and they said sigma. sigma C over 3. And this we're looking to try and pluck out values which will be Newton meter squared. No, I'll just leave it like that. Leave it like that. Right, so we've now got a target to aim for. 1.5. There is refinement needed here, but we've got a rough target to actually aim for. So this is nice. We've got something we're aiming for. We've got all those variables set up. In fact, because we're modelling this way, it means we can play around, we can change things, we can go crazy with this. I love this, as my enthusiasm should well show. Okay, first things first, we need a material. Without material, it's going to be a bit crap. Oh no, sorry. What we need to do is tell the system where we're going to be contacting. We need to tell the system that there are contacts there and it interfaces a particular way. So let's get on to definitions. I'm going to right click, I'm going to go pairs, and I'm going to go contact pair. What this now does is says, in your drawing, are any of these bodies actually separate bodies that interface with each other? Now, because we've done 2 separate parts, there is. If we don't do this, it penetrates through the actual system, wrecks what we're trying to do. So I'm going to say my source body is this. My destination target body is the lower point here. And let me have a look. So my search method, I can do a fast, clumsy, quick response. I can do a direct response where as long as it comes into face, it'll start to give reaction. Now, I often find this contact system tricky in many ways. As a reflection, I still favour ANSYS a little bit on its contact methods. I'm sure a lot of people will shoot me for saying that because my PhD was in this. I love this particular software. But in between the two, I do still find the contact method a bit better. Said something better! I do find it a bit better, so I do prefer that side. But it is really what it is, really. I do find a lot of strength in that, but let's continue. So let's get down to materials. Oh, sorry. So let me get onto materials, and what we're going to do, we're going to right click and we're going to go blank material. Now, because what I've just put in, it instantly says you put a blank material in. These are the variables I need to be able to continue. Do you have these or not? And because we're doing two separate shapes, two separate materials, what I'll do is I'm going to go blank material again. And for this one, I'm going to go E1, going to go V1, going to go D1. Then instantly what I've got is, I've actually got that running. Now you'll see there, if I go there, there's no options there. What the hell's going on? If I go onto my sections here and I just remove that as an option. Whoops, not that one, like that. So then on my first section, I'm going to remove that. That's better. For some reason it just wouldn't do it. And I come back, and now if I go back on and choose that, it instantly says, right, you've done that. Now populate what you need. So what we'd said is that E2 was going to be our Young's modulus for the second material. V2 again, Young's modulus for the second material, and D2 again for the second material. So now we've got the two materials interfacing. You'll know that there's no marking, no complaining, so it means everything that's in there is good. If you've not done so far, make sure that you hit save. So I'm going to save myself. I'll call this Hertz problem. So this is a classic problem, but so now we're into that position. We've now assigned some contacts. Ooh, we've assigned contacts, fantastic. So what we'll do on here is we move in, and the first things first, let's decide how this thing's working. Now in the classic Hertzian problem, force travels on the Y in the negative direction. Granted, at the minute I've not calculated the indentation. I will be putting that on the notes because at least then you've got the full set. I was just looking for a value to verify in this problem. You can calculate that in there. I just wanted to show you more contacts. Right, so what we can do now is I'm going to right click and I'm going to go fixed constraint. So within my fixed constraints, I'm going to go to each edge of the fixture. That's now fixed, and that's purely because, don't forget, the force is traveling that negative Y component. So the lower half elastic is not going to move. That's the classic problem. So let's move on to the next. We know we've got that in place. So I'm going to go boundary loading. I'm going to choose round the actual boundary itself. And I can either go Newton meter squared for the force units, or I can go total force. Now with my total force, because I know what that's going to be, I'm going to say minus F. So that minus F now has a force moving downwards. Again, the one thing that frustrates me with this, I know a lot of people will say, well, yes, you're academic, you should know. It would be nice to get some directional input. Arrows even. I can add arrows in, but that little bit of an indicator does make it much easier for people to navigate around. I mean, I can navigate it, not a problem. But when you're first really getting to grips with this software, it would just add that little bit of ease for you. Right. Finally, the last thing that we've not added is we've not added anything to tell it that it's actually to take into consideration these contacts. So I'm going to right click. Then I'm going to go to pairs and let's go. Oh, where are we? Oh, contact. So we go onto the contact pair, and what I'll do is I want that to be seen first. So I'm going to put that up there. So you see there, contact pairs are in there, so it already knows what it's doing. It's going to be picking that one up. Penalty factor. You can present for stability. For the present state for stability, or we can say manually tuning, so you can put a failure factor onto it where the penalty multiplies out, and once the contact's made it will fail under different states. or we can do user defined, where it will actually extract what it's using for the present factor. You can modify this. You can change this. But what I'm going to do is not. I'm going to leave it in this state. And I'm going to leave it in that solution. So, finally, as ever, we've got everything there. Let's build this mesh. And the mesh is quite clumsy. Large chunk sections. You just kind of think, not convinced. Within here, I could do mapping, I could do scaling, I could do lots of refining. What we'll do is we'll run under a standard meshing procedure, or we could go adaptive. Oh yeah, we could. No, let's stay with this first. And what I'll do to try and clean it up slightly is I'm going to make it an extra fine build. So I'm going to build it, and that's what it gives me. I've gone to extra fine. I'm still staying with tetrahedral. Arguably, really, this should not be tetrahedral. This should be quad, given the shape that it is. Tetrahedron in a circular structure, okay, yeah, then fine. But on a square tap structure, we'd really want that to be quad, and that is probably what I'll do moving forwards. But first things first, let's get a solution. Let's take a look at what we're looking at. So I'm going to go to, now, if I hit run, it's going to run on a particular state, single state. If I want to look at a gradual build in stress and force across something, there's a few ways you could do it. We could do a parametric study. We could run it under a variable that we've still yet to name, and then systematically record that position every time it iterates to see what's happening, and then record them states and then map all them states together to give us an overall of what's happened. So what I'll do first is I'm going to come up here, and I need a timepiece. So I'm going to call this para, just because we're saying parametric study. I'm going to set that 0. This is purely a dimensionless thing. This is a unit driven thing of what, not unit, this is a value driven thing of where there is no units attached. So it's something for me to use as a variable. I'm trying to think of the best way of describing it. If anybody has a better way, please let me know, because I'll obviously adapt to that. Bring that up, bring that up, bring that up, and that's what we got. So let's get back onto here. Now, a few ways to actually achieve this. What we got here is we've got results while solving. What do we want to see? We can plot. Excuse me. We'll come back to that. But first, because this is going to solve so quick, it almost seems pointless. Variable sets. We've got mesh selection. We've got adaptive. Then we've got study extension. Study extension's very interesting. So now with the study extension, what it's actually saying is there a type of sweep process you want to do? Answer is, yeah, there is. So I'm going to go sweep. I froze a bit then. I'm going to sweep. I'm going to add. Now look at that parameter. It's instantly brought in the Young's modulus. This is because all it's doing now is it's reading directly from the parameter names that I've got loaded in. If I expand that, got all my parameters and para. Nice. So within my para, what I'm going to do is I want to set a range. I'm going to open that up. Where should we start from? As ever, let's start from 0. Then we're going to increment by 0.01. 0.01, I have to just double check that. And then we're going to result at 0.28. Just a nice overall. You'll notice no units on there because this is totally dimensionless to it. And what it will do is it's going to increment itself and run intermittently at 0.01 until it meets 0.28. So be aware of this, because I've had people who put an increment that's bigger than your output. And you go, it don't work. You go, you're damn right it don't work, because it's wrong. Right. And I'll extend on my units. I'll extend on my results. And let's see what we get. So let's run. Or compute. You'll know now that I just hit pause because I was cheating. That actually doesn't take long to solve. I was just using some hotkeys, just getting used to them. So we've now got a solution. We've got our interface. We've got that Hertzian behavior going on. I'm not really convinced with the mesh, but it gives us a good insight for a starter. Gives us a good insight as to where it's going. I mean, what solution did we choose on that? Extra fine. It's still quite chunky. But what it can do is it can start to tell us, are we on the right ballpark? That's what's important. Are we getting close to the right solution? So first things first, let's extend it out. We've got contact pressure. Contact pressure at 0, yeah, because we've actually got nothing assigned with it. So I'm just going to, this is from an old solution actually. So I'm just going to disable that completely because I don't want that. I'm actually wanting to focus around my surface. So if anybody's wondering, by the way, that we've got practically a strong base material, so this can be aluminium, steel, that are interfacing with each other. If I go to deformation, you'll see there that the scale factor is set to 1. However, if I set that to 100, in fact, if I drop off the scale factor completely, then run it, what you see now is this massive over-the-top exaggeration. And it's just to show that it's actually travelling. What I'm going to do is set that back to 1, because given the nature of what we're doing, it's all about this behaviour here. It's all about the Hertzian response. Now, the important thing that we're looking for is, we are looking for equilibrium across. If you look upper, you look lower, it is actually moving as we want it to. As it solves, we're into that megapascal area. Oh, Newton meters area. So is it mega? I don't think it is mega, is it, to the power of 5? But anyway, what I actually want to know is our value similar to what we've calculated? So we were looking for 1.5. 1.5. So we're looking for 1.5, and this just gives us an overall. So this gives us what's going across the whole thing. What I'm actually interested in is knowing what its maximum and minimum is. So let's get back in, and what I'll do is right click. Oh no, let's do this differently. Select it on the surface, gonna go to more points, come down from my more points. There's a few things we could do. Go max and minimum to the surface plots, max and minimum to a point in itself. We can go max and minimum, well, let's just go max and minimum surface plot. No, in fact, I want the point. What am I talking about? Because if I come back, you look here, we've got these 2 points interfacing. So what I'm actually interested in is the point of this. So it should give me that key area of where they've interfaced. So I'll just delete that. Oh, excuse me. Winded today. Come back in, and I'm going to go points, max, min, point. And then let's run it. You go, brilliant. What's that giving me? And you go, oh, hang on a minute. All it's done is it explained how much it's moved. Oh, it's because it's in displacement. That's the one thing that irritates me. You go onto the max and min, it will always default itself there. You think, well, I've actually got that on there. If that happens and you just think, damn it, copy from your plot of stress, and then let's just get into here, and let's do the same thing again, and then let's plot. Ah, nice. So, right, so the result, 5.5 is massively out. Massively out. The systematic process of the force it's applying should not be so high. So what's gone wrong? It's a continuous force. Force is just building as it's just been applied to it. So what we need is a gradual increase to give us a true representation. And you look there. I did this. This was my mistake. See how we've got minus F? That just continues that force continuously. So what I want to do is do an incrementive build. So I'm going to go open brackets, para, multiplied by my force. And then I'm going to come back and run it again. Right, so when we've run now, I've literally just paused then because I was thinking, why has that been going on? You look at this, which is the power of 4. We're looking for 1.5 to the power of 5. We are out. In short, we're very much out. Let's revisit the mesh. Now, I want to go into a bit more of a depth on mesh. I think the next video I'm going to do is about why we do what we do. So if I zoom in, we're talking about 1, 2, 3 nodes of contact between them. A little bit big, a little bit too much. It's distributing this across this single point here, and we've obviously got about 2 by 2 matrices for our stiffness matrix. So it's not a very accurate representation, as when you look at it you go, wow, that's amazing. It's actually not very good. So we're going to test that theory, and I'm going to come back and I'm going to drop this to extremely fine. I'm going to go to the finest it will go and see if this gives us somewhat of a more accurate representation. You'll also notice as well that I came away from using the study extension and I've just gone to using a parametric sweep. It's the same thing. With parametric sweep though, I can have study extension in there and run a parametric sweep of a range of that study extension that I've added to it. So in this case it's the same thing. We did this for the dog bone, if you remember, different variations. Just a reminder, I can right click, go parametric sweep, and then that's introduced, and all I've done is added para. So what I'll do now is I will run. It paused me then because I wasn't sure, because we're a factor of, well, 10 out, 10 plus out. So that can be concerning. If you get them types of values, you come away and go, that is definitely not quite right. So what we need to do is fix what's going on. So that's what I've just been doing. Just been looking to see where I've gone wrong. Because you look there, I'm at 79082 Newton meters, and I'm wanting to be at least be 15. So yeah, that's not what I really wanted. There's quite a large section out really. So I'm running through again on an extremely fine. I still think that this is going to give us a result that's still out, but it will give us that indication if we are on the right boat. Because if you think about it, between them 2 points where our surface area interfaces, what we get, oh look at that, what we get is something a little bit more accurate. So let's see where we are. Going to this, we're at 1.54 to the power of 5. So according to our theoretical solution, we're 1.56559 to the power of 5. Which is a phenomenally good solution. It's great where we want it to be. It gives us a lot of good, solid insight that particular area is something that we can look at a little bit more. Now, what I can do with that, I can do all sorts. I could put variation into there. Now, if we want to know the stiffness, we do need to go revisit back and add in further elements to it. Because at the moment, all I've done is taken into consideration the cylinder. Just the cylinder. there is a further equation to equate both Young's modulus and Poisson's ratio. I will be putting that into the notes, and my aim is to evaluate this and to go that extra one step to try and integrate that into it as well, so we can then look at the stiffness between the two, well, more of the contact force between the two, and we can also look at coefficient of friction, start to really build it up and get that tribological interface, which a lot of you guys will be doing with TED. But yes, that is contacts. That is the classic Hertzian problem, or at least the beginnings of the classic Hertzian problem. If you've not done already, please save it. As ever, if there are any questions, if there's anything you're unsure about, or you're just fascinated with doing it this way, or you want more insight to COMSOL, please let me know. I should point out, COMSOL is actually not our main focus of weapons of choice in these classes. My idea this year is to give you guys a real option of this is COMSOL, this is ANSYS. I am actually also tempted to incorporate a little bit more with SolidWorks. Then at least then you've got a variation of all. The only thing that I've not done yet is a big session on meshing, which I do intend to do. There is already videos there to support for ANSYS, but I want to have a bigger, wider scope. So let's pick up on why ANSYS is praised for what it does. Because ANSYS, as far as a mesher goes, the adaptive processes that's on there, they're really good. They're really, really good. Thing is, with COMSOL, it won't do it automatically. You've got to build it in. So this becomes like your weapon of choice, if you will. You kind of choose what you prefer. The thing is, with SolidWorks, it is constricted and restricted purely to tetrahedral mesh, which is not a problem, but it can prove to limit you if you're wanting to do a lot more of really in-depth simulations. The beauties with this, with COMSOL, is you can build meshes yourself. You can say, this type of mesh, I want it to be like this, and it to continue along a flow. So you almost model the mesh. With ANSYS, ANSYS has an adaptive process, which then you can build on the top of that. So it just becomes your real weapon of choice. So you see here, this in ANSYS is what you would see as the default mesh. If I right click on here, we are going to do more on this, but if I left click onto it, you'll see there, sequence type, physics controlled. Now if I drop that and say user controlled mesh, what you'll see is it brings it down to something that we've all seen before. Freedoms like this. In fact, I was going to say this is the end, but let's not. Let's just keep going. Let's do one more set. Let's do one more piece on this, because it is fascinating stuff. What we'll do is I'm going to, as I was theorising earlier, the circle's quite good for tetrahedral. So if you look, the triangles do give a good representation. What I'd like to do is perhaps incorporate adaptive on here and here. Let's face it, it's a block. We know that's going to be quad. The idea of using 4-point nodes, an idea of the way 4 nodes will interface with to make, in a lack of better words, a brick, is really useful. So what I'll do is, first things first, I'm going to do a free quad. It kind of goes, okay, I'm a free quad. What do you want? So I'm going to bring that up. And you see there it's set to remaining. I actually don't want it to be remaining. I'm going to go domains. Then it says, okay, you've chosen domains. What domain do you want to quad? I want to domain this one. So now, if I right click again, see what you'll see here is I've got sizes. Everything is set to extremely fine. We might not even want that neither. So I'm going to right click and go to size. You see now we've got 2 points here. This size controls this remainder. This size controls the quads. So what I will do is I'm going to say, let's just go fine. And let's just see what happens by hitting build. Now you see there what we got is we've got a basic. That's set to normal. So let's go extra fine. Extra fine. Let's go build all. See, now what we can do is freely move around. This is quite nice. Quite nice. So then I'm going to set my quads. I'll do an extra fine on the quads as well. So let's build all. And you go, okay. Let's go extremely fine. Then what we've got is a good representation for our half elastic. You look at where the points interface, look where the nodes are facing. We've got split in between both of them tetrahedrals, which is good. We've got that representation for response when the tetrahedral starts to interface. Now, really up here, I'd like to form an adaptive behavior. So I'm going to right click. I'm going to go to more options. And I'm going to go adapt. Now what it looks for is it's saying, right, well, do you want to go the whole geometry? Or do you want to go one particular geometry? I'm just going to go domain. Which domain do I want to make adaptive? This one. And let's just go solution types to last. And error expression of 1. Well, we'll start with that and let's see what it gives us. So let's build all. You look there, see what we got here? We've got combinations of tetrahedral and we've got standard tets that change. We've got some quads forming. We've got a rebuild of particular areas. Now you see there that I'm on set to extremely fine. But if I bring that back a little bit, oh no, sorry, that's my quads. If I bring that back and then I'm going to set that to, let's just set that to fine. So build again. There we go. Okay. So if we go normal, we see now is we've got these changes to give us the best representation. So without further ado, let's see what types of solution it will give us. Okay, oh, let me just close that. Apologies, I was looking at something else. Right, so the reason it's taking so much longer now is we're going to get a lot more of an in-depth. Now, if you look at the bottom, you see the memory that's been allocated to this calculation. And we can see now we're starting to get a lot more of convergence needed. Now I get an initial solution of 1.56. So you look at that actual beautiful output there. So we've got 1.56. Let's see where we are up to. Look at that. 1.5. If you round up because of the 9, 1.56. Still error there, but we are so close. It's crazy. Right, so that's brought that error down, and we've done that little bit more of sexy adapting. So if we look where we're up to now and look at what we got here, it's, you know, we're really starting to build up a lot more of an in-depth simulation. We are going to do a lot more with meshing because this is not just a single thing to do. We need to keep going and reiterating and seeing the difference as to why we do what we do. Anyway, as I said before, if there are any questions, if there's anything you need, please either drop me an email, come and find me if we are back on site. You can message me over Teams. I'll gladly meet up with you and we can go through more of this. If there are any further reading that you want from this and anything you want to know about this, please let me know. I will more than gladly help. And if not, I will speak to all you guys soon. Thanks.